Okay, so this is for problem number 11 for the chapter 26 problem set for week 1. Problem 11 asks, 3 positive particles of charges 11.0 microcoulombs are located at the corners of an equilateral triangle of side 15 centimeters. Calculate the magnitude and direction of the net force on each particle. So I've drawn out the figure they gave us, 3 positive charges, each 15 centimeters from each other, forming an equilateral triangle, each with 11 microcoulomb charges. So to begin solving for the magnitude of the force on each charge, we can begin by looking at one charge, this charge in the bottom right hand corner. This charge in the bottom right hand corner has 2 forces acting on it. We can go ahead and call each of these charges, call the top corner A, call this one B, and call this charge C. Now we can talk about the forces that are acting on charge B. So the first force we have is the force of charge C on B, and the second force on charge B is the force of charge A on B. These two forces acting on B should have the same force magnitude that we can calculate using Coulomb's law. Force is equal to K times Q1 times Q2 over R squared. And we'll come back to adding a direction to those forces when we finish the problem. So to begin to solve for this problem, we need to find the magnitude of the 2 forces acting on charge B. So to do that, we solve for the force using Coulomb's law. So you can plug in, we have a constant 9 times 10 to the 9th times the charge on each of these is 11 times 10 to the negative 6th because it's in microcoulombs, but we want it in coulombs. And charges A and B, or C and B, have the same charge magnitude. So we can just square this value. And then the distance between any of these forces, any of these charges, is 15 centimeters, which we want to convert to meters, so 0.15 meters. And we can solve for that, and we get a force acting on charge B, force C on B or force A on B, to be equal to 48.4 newtons. So this is equivalent to force C on B and force A on B will both be equal to 48.4 newtons. Because charges A and C have the same magnitude of charge, and they're both the same distance from charge B. The only problem is to find the overall net charge of the magnitude. To find the overall net charge on particle B, we have to find the overall charges that forces A and force C, the particles A and C exert on B. So to find the force from particle C, we already solved for it. It's the force of C on B. This is in the positive x direction, so it only has one component, and that's 48.4 newtons. To find the force from A, we have to work a little bit harder because the force on A is not in either the y or the x-axis. It's made up of 2 components, so we can solve for each of those components using trigonometry, or just geometry. The force from A, we'll just draw the overall force down here. This is the force of A on B, and it has 2 components. Its x component and its y component. Now, because this is an equilateral triangle, we can determine the angle on the inside here is 60 degrees, which means the angle between the x-axis and the hypotenuse should also be 60 degrees. And we can use that to solve for each of these components. Now the measure of the hypotenuse is the force magnitude we found earlier using Coulomb's law. And using geometry, we can say to solve for, let's say, sine of 60 degrees, we would take y over the hypotenuse, 48.4. So y will be equal to 48.4 times sine of 60 degrees. And we can do the same with x, except with x we'll be solving for cosine. So 48.4 cosine of 60 degrees. And these will be the force of A in the x and the y direction. So when we solve for these two values, we get the force on y is equal to 41.9 newtons, and the force in the x direction is 24.2 newtons. Now that we have our forces in the x and the y direction, and we have our force from particle C in the x direction, we can find an overall force. So the net of the forces on particle B in the x direction will be 48.4 plus 24.2, which is 72.6 newtons. This is in the x direction. And then in the y direction, because the only force acting in the y direction is in the downward or the negative y direction, we have negative 41.9 newtons in the y direction. So in vector notation, this is 72.6 I minus 41.9 J newtons. But they wanted the magnitude. So to solve for the magnitude, we take the square root of the square of each value and solve to get 83.8 newtons. So this is the magnitude of the force of particles A and C acting on B. Now the question also asks us to determine the direction that the force is acting on each particle. So when we look at particle B, we have the forces A and C, both equidistant from particle B at 15 centimeters, both with the same repulsive force of 11 microcoulombs. So we can say that the overall forces from the force of C on B and the force of A on B give us a direction of the overall force on B going away from the center of the triangle formed by the three particles. So we can say that this force is equal, the magnitude of the force is 83.8 newtons, and is moving the particle away from the center of the triangle formed by the three particles. So we've solved for the magnitude of the force acting on B, we've solved for the direction of the force, and now we can say, rather than going back and solving for each particle A and C, we know that particles A and C will also behave like particle B. So on particle A we'll have particles C and B, both repulsive on particle A, with the same magnitude of charge and the same distance from particle A. So particle A and particle C will also both still have the same magnitude and the same direction as particle B that we just solved for. So by solving for particle B, and knowing that these are all the same charged particles, or not the same charged particles, but particles with the same charge, and the same distance apart from each other, they should all have the same magnitude and the same direction. So this answer here solves for all three of our particles. And that's how you do number 11.